My name is Brian Neyenhuis. I'm the director of our commercial operations group at Quantinuum, and today I want to talk about our trapped ion-based quantum computing hardware. So Quantinuum is sort of a new company. We were just formed this last November with the merger of Cambridge Quantum and Honeywell Quantum Solutions. Together, that's Quantinuum, and we've got offices here in Colorado, where I'm based, along with Minnesota, in the UK, Germany, and Japan as well. Working on both quantum hardware using trapped ions, as well as quantum software and quantum algorithm development. So the center of our quantum computer is based on trapped ions. Here's a picture of our trap, where we grab onto these ions and manipulate them using this surface electrode ion trap that we fabricate up in Minnesota. And we follow an architecture that was proposed quite a while ago by the NIST Ion Storage Group, just up the road from me here at Boulder. And they proposed at that point that you could build a large-scale quantum computer using trapped atomic ions because they're easy to grab onto with electric fields and move around. So by fabricating some complicated electrode structure, you could physically move your qubits around, move them in and out of dedicated zones for high fidelity single and 2 qubit gate operations. And then you could scale this up by adding more and more zones. And this was, they coined the phrase back then that this was this QCCD architecture, this quantum charge coupled device, making the analogy between how these ions are moving around within this complicated quantum computing device and how electrons are shuttled around at the back of your CCD sensor, say in the back of your digital camera. So we follow this architecture. Here's a schematic of the trap that's in our current commercial systems. All of our qubits sit in a line here at the center of the trap. And then all the various electrodes, which are shown here in different colors, shuffle these qubits around, moving them in and out of the interaction zones where they interact with the laser beams to do quantum gates, as well as reconfigure the ion chain, ordering and pairing up the qubits however we want to execute an arbitrary quantum circuit. And I would say that this commercial computer we have now integrates all the necessary ingredients that were proposed back in this paper by the NIST group, and has all the ingredients for a scalable quantum computer, even though it is sort of a small system at this point. So I'll brag a little bit about the QCCD architecture and some of the advantages it has. The first is that it natively has all-to-all connectivity, that because our qubits are completely reconfigurable, we can move any two next to each other and perform a quantum gate in a single step. And this is a great advantage over, say, architecture with fixed geometry and local interactions, where you might have to do a series of logical swaps, each with error, to get information from one side of the device to the other. Here, you don't have to worry about the geometry of the trap because it's reconfigurable. We can move the qubits at will. Say it also has very high fidelity gates because our qubits are always isolated and moved into specific zones for these quantum operations. We can have very high single and 2 qubit gate fidelities, as well as state preparation and measurement. But I think an important thing to point out here is that this high fidelity also stays as we scale because this basic building block remains the same. We don't have to worry about extra crosstalk because we're just scaling up the classical control around the qubits. The basic interactions between the lasers and the qubits stays the same. So we expect these fidelities to stay high even as we scale. And then the last feature I'll point out today is that it also gives us a very straightforward ability to measure a qubit in the middle of a quantum circuit and then reuse that if we want. So we can, because the qubits are mobile, we can move just the qubits we want into the interaction region and measure them while all the other qubits are out of the way, and their quantum state can remain intact even as you measure some subset of qubits in the machine. So this can help us efficiently use ancilla qubits over and over again by using them and then resetting them and using them again. It also allows us to do conditional logic, where you can measure something in the middle of a circuit and make a decision while the circuit's still running, so a quantum if statement, if you will. And this is an essential ingredient that everyone needs to develop to get to quantum error correction. You need to be able to measure syndromes and feedback to them in real time, but it's quite straightforward to do because of the mobile nature of our qubits. So if you have quantum circuits that you're ready to run today, there's a couple of very straightforward ways to gain access to our machine. Oak Ridge National Laboratory has a quantum computing user program that you can apply for, just a short proposal on the project you're trying to do and gain access to the machine, as does Azure Quantum. They have their credits program through Microsoft there that you can gain access to the machine in very short order. If you're not ready to write your own quantum circuits or want to talk more about applications or help with algorithm development, this merger gives us lots of teams across the company with expertise in all sorts of subject matter. You should contact us directly at qcsupport@quantinuum.com. Thanks.